Okay, with this unit, we're going to look again at reactions, chemical reactions in particular. And we have been, up to this point, dealing with the idea that reactions run in one direction, that reactants are turned into products. And when all of the reactants are used up, we don't make any more products and the reaction is done. In many cases, that is true, but in just as many cases, that never, ever happens. There are reactions in which the products are never done being made and the reactants are never fully used up because both reactions are happening. The reaction that goes from reactants to products is occurring just as it always has, but there's also another reaction, we call it the reverse reaction, that turns the products back into reactants. And it's the balance between these two, the forward reaction and the reverse reaction, that we want to look at. And when we have reactions that are at a balance point between those two reactions, we say that those reactions are at equilibrium. So that's where this unit comes in. We no longer are going to look at just reactions that go to completion. There's no such thing as a limited reactant. In chemical systems at equilibrium, both the reactants and the products are going to be there at the end point. And we need to learn some new rules and a little bit of math in order to be able to calculate how many moles of everything we'll have, because we can no longer use kind of a limited reactant approach like we did in grade 11. Okay? So just thought we would start by going through a couple of examples of what we even mean by equilibrium reactions. This diagram may look a little complicated, but let's just work our way through it. Basically, what I'm trying to show here with this diagram is the equilibrium reactions that exist between the atmosphere. So we've got the air, which represents the Earth's atmosphere, the water, which would be lakes and oceans, the water that's covering the Earth, and then the rock that's on the bottom of those oceans or the bottom of those lakes. Okay, and we're going to focus on some key materials here. The one thing I guess we could call a reactant would be this one. So we're going to talk about CO2. And CO2 exists dissolved in water as an acid. So this is H2CO3. So this second reactant or second chemical we're going to look at is called carbonic acid. And then finally, through a somewhat complicated pathway, we get down to a third source of carbon, which is in the rock, which is calcium carbonate or limestone. So I'm going to simplify this a little bit. You can notice there's a fair bit of chemistry going on between the CO2 and the calcium carbonate. But let's just take a look at some of the main things here. What we know now is that the reaction between CO2 and, this is just CO2 being dissolved. So the wave action, the waves kind of help to dissolve some of the CO2 into the water. And that dissolving process turns CO2 gaseous in this direction into carbonic acid. And the amount of CO2 that goes into the ocean or into the lake and turns into carbonic acid is based on the concentration of CO2. When we have the H2CO3, at the same time that CO2 is being dissolved in the water, we also have H2CO3 or carbonic acid breaking apart, turning back into water and CO2. So these two reactions are working against each other. We call the first reaction, let me do it in red here, the CO2 gaseous goes into CO2 aqueous, but then it quickly becomes not just dissolved carbon dioxide, so we're just going to leave that step out, and it quickly becomes H2CO3 or carbonic acid. Okay, so let's put the water in here just to make that a little more clear. So the water and the carbon dioxide combine to make carbonic acid, and we call that the forward reaction, at least the way we have it written right now. Okay, and that occurs at a certain rate. We just finished talking about rate, so there is a certain rate at which H2O and CO2 will turn into carbonic acid. If you increase the amount of CO2, that rate will go faster. If you decrease the amount of CO2, that rate will go slower. So just same ideas we were talking about in the previous unit come into play here. Now, the reverse reaction that also exists, and this is new, we've not ever had reverse reactions before. The H2CO3, the carbonic acid, is turning back into CO2 and into water. So we call that the reverse reaction. At least in this way, the way we've written it, we've written this one as a forward reaction. Left to right is considered forward, and right to left is considered reverse. And that reaction occurs at a certain rate, and it's dependent on how much carbonic acid is in the water. The more carbonic acid there is, the faster the reverse reaction goes, and the more acid gets turned back into CO2. So there's a balance set up here between the CO2 and the H2CO3. Eventually, the rate of the forward reaction, so the rate of the reaction producing carbonic acid, becomes equal to the rate of the reverse reaction, the reaction that's turning the carbonic acid back into CO2 and water. And those two reactions seem to have stopped. But if we could look at the atoms kind of on a microscopic level, we would see that this is still turning into CO2 and water. And we would see that the CO2 and water is still turning into H2CO3, but it's happening at the same rate. And so macroscopically, with our eyes, we don't see anything changing. The pH wouldn't change of the ocean. Nothing would change. But at the microscopic level, molecules would be going back and forth through these two reactions, just keeping and maintaining a balance. You can imagine it's like if you're sitting in the classroom and one person walked into the room and another person walked out of the room at the same time. We have the same number of people in the classroom at all times. As long as the people going out equals the people coming in, then we see that the classroom is at equilibrium. We see there's no change in the numbers of people. But if we speed up one of those reactions, then we can start to lose people in the classroom, or we can get more and more people in the classroom depending on which reaction is going faster. That's kind of at the heart of what we're going to do in the next few days, is take a look at what controls these reactions and what causes the forward and the reverse reactions to go faster and slower. Now, I bring this one up, Tim, simply because of global warming and climate change, the idea that we're putting more and more CO2 into our environment. That's making this forward reaction go faster and putting more and more acid into our oceans. And that's why you've probably talked in other classes about the acidification of the ocean. And the oceans are becoming more and more acid because this equilibrium reaction has actually been disturbed. It's not in balance. The reverse reaction is going slower than the forward reaction. Because we've got this buildup of CO2, this forward reaction is going much faster than the reverse reaction. Now, eventually it will come to a balance again, but that balance will be at a much lower pH. There'll be much more H2CO3 dissolved in the water before that rate of the reverse reaction gets going fast enough to balance out the forward reaction. So what we see is acidification. We see the pH of the ocean going down, and that has all kinds of problems. It affects anything that grows a shell in the ocean because the acid gets in the way of these carbonate ions, and shellfish use the carbonate ions and combine it with calcium, just like this reaction here, showing how that limestone is made. Calcium and carbonate form limestone. When there's a pH drop, this reaction gets slowed down and it gets inhibited. And so rock is not formed, which is not a big deal, but it is one way we sequester CO2 is by putting it into rock. But more importantly, if you have your lobsters or clams and things that are sitting down here living in the ocean, they have to make a shell, and they can't make that shell very easily as the pH drops because it gets in the way of this equilibrium that allows them to make calcium carbonate. Okay? So there's all kinds of things that go on with acidification, but basically one of the things we need to remember is that climate change is causing a disruption of this equilibrium and resulting in more and more CO2 being put into the oceans and then lowering the pH of the ocean. Okay, so I'll post some other information about ocean acidification. You can, a couple of videos and things so you can get a better handle on that, but it's just a really good example of the kind of reaction where there's a forward and reverse reaction. And those reactions are typically in balance, but they can be disrupted, as they are in this case, and they will continue to be disrupted, one going faster than the other until a new balance is achieved. And that's kind of the chemistry we want to take a look at. How do we achieve that balance, and what does everything look like? How much of everything is there when we achieve that new balance? Okay. Now, another thing to remember about chemical equilibriums is they have to occur in a system in which there is a closed system. Okay? Now, I know I just talked about the ocean. The ocean might not look like a closed system, but just wait a minute and I'll think I can show you that the ocean and the atmosphere is a closed system. If you take some calcium carbonate and put it in a beaker, and then you heat that calcium carbonate, it will turn into calcium oxide and CO2. That will happen, but that reaction will go to completion. The calcium carbonate will completely decompose with heat and make CO2 and CaO, because this beaker is considered to be an open system. An open system means that products and reactants are free to leave or come into the system. There's nothing keeping them from leaving, and there's nothing from keeping new stuff from coming in. So as the CaCO3 decomposes, that CO2 just leaves the system. It goes out the top of the beaker. And we would see this thing go to completion, and that's where we could do our quantitative kind of, last year we called it stoichiometry. So that's where we could do the stoichiometry and we could figure out, if we started with a certain amount of CaCO3, how much CO2 were we going to make. What happens at these reactions is we take the same kind of reaction, but instead of having an open system, we put a lid on this thing and we close the system. So we have the same CaCO3, calcium carbonate, sitting on the bottom. We heat it. It turns into CO2 and CaO, but that's only one of the reactions that happens. Because this system is closed, the CO2 hangs around. And eventually the CO2 and the CaO, carbon dioxide and the calcium oxide, they start to react with each other and reform calcium carbonate. And so we get an equilibrium reaction. We get a balance of how fast this is turning into CO2 and calcium oxide, and how quickly those two products are turning back into the reactant. And because it's a closed system and nothing can get in and nothing can get out, we can finally get this balance achieved. On this side, over in the open system, the forward reaction, so we could say the rate of the forward reaction is so much bigger than the rate of any reverse reaction, because we keep losing all of the reactants. The CO2 just disappears. On this side, though, we do get to a point where the rate of the forward reaction, making the CO2 and the calcium oxide, will come to be a point where it equals how fast the CO2 and the CaO is turning back into calcium carbonate. And so in this closed system, the calcium oxide or calcium carbonate will never completely decompose. It'll always be present in some ratio. And that's one of the things we'll do probably next week, is take a look at how we can use stoichiometry to figure out what the ratio is of products to reactants. So we can actually do all of our stoichiometry. We just have to do it in a slightly different way. Okay? And that closed system has some limits on it. You need to understand what temperature that system's at. We need to understand what pressure that system's at. We need to know the concentrations of the reactants in the product. All of those things factor into what the balance of rate forward equaling rate reverse is going to be. So it's a little trickier, but not overly so. And we will work our way through kind of how you deal with figuring out the balance point between these different kinds of reactions. Okay. Maybe just one last example in this video, just to give you something a little more common to think about. So if we were to think about a bottle of pop, you've got an equilibrium reaction existing inside this bottle of Pepsi or whatever kind of beverage you want to drink. in the top here, there is CO2 gas. And that's why the bottle is under pressure. There's CO2 gas that's been released out of the solution. It was put into the solution to carbonate the drink. And some of it comes out of solution and then fills up this gap in the top of the pop bottle as a gas. At the same time, there's a whole bunch of CO2 still sitting in the pop. Down in here, it would be AQ, it would be dissolved carbon dioxide. And as long as it's a closed system, these two things sit at equilibrium. There is CO2 coming out of the pop and turning into a gas at the same rate that there's gas coming out of the airspace and going back into the liquid. If there wasn't, and you did something to disturb this, then the pressure up here, for instance, we shake this, we can increase the rate of this reaction going from aqueous to gas. So let's just label these. Let's call this the reverse reaction and the forward reaction. If we shake this bottle, we can speed up the reverse reaction and turn more and more into gas, and that increases the pressure in the top. Eventually, that could cause the lid to fail and the bottles to explode. You could do the same thing with a can of pop. If you were to shake it enough, the little seal around the pop top lid would eventually fail because you were increasing the amount of CO2 by shaking up the can. But as long as it stays closed and we don't change its temperature and we don't shake it up, there's this balance point between the CO2 gas and the CO2 aqueous. Okay? So that balance is normally there as long as it's a closed system, as long as the bottle is closed. But when you open it, now this reaction changes. Instead of having a reaction that's going backwards and forwards, we have this reaction that's only going in one direction. We have just aqueous CO2 turning back into gas. And we see that as soon as we pour the pop into a glass. The bubbles start to come up, and that's the bubbles forming of the CO2 in the water turning back into a gas. If we leave the top off, that will go to completion, and eventually we'll have flat pop. All of the CO2 will come out of the pop because the reaction is basically going mostly in this forward direction. It's mostly going from aqueous to gaseous. So the only way we can prevent that is by putting the cap back on. And if we were to put the cap back on the pop, then the two reactions that are competing against each other eventually come to a balance point again. Initially, the CO2 is going much greater in this direction and only a little bit in that direction. But as time goes by, this reaction starts to slow down because we're using up some of the CO2 that's in the pop. This reaction starts to go faster because we're making more CO2 in the gas form. So that reaction speeds up. And eventually the forward reaction and the reverse reaction become equal to each other, and we don't see any bubbles in the pop anymore. But every time you open it, we lose some of the CO2, and then when you close it again, we have to reestablish that equilibrium. And that gets harder and harder to do as there's less and less pop in the bottle, and eventually the pop will go flat. Okay? So whenever you seal the bottle, though, that gives a chance for that pop to reestablish an equilibrium. But because you had a time when it was an open system, then some of that CO2 has been lost, and eventually, since you're losing reactants as we go along, you'll no longer be able to achieve that equilibrium, and your pop won't have any fizz anymore. Okay? So that's just a few examples of things that we're trying to talk about in terms of equilibriums. I'll post some of this information about bubbles in beverages. There's a good video there for you to watch. If you've ever been stuck with someone who's given you a can of pop that's all shook up, I'll post this video as well, and Steve Spangler will show you how to open the pop without making a mess. So I'll post that video as well, just as another one to watch. But for now, hopefully that gets you started on doing some thinking about equilibrium and kind of understanding the difference between that and our normal quantitative reactions where we go to completion. Okay, thanks.